Chapter 1, show me what you can do. It's not up to me, it's mostly up to you. That's not really true. I made this video for you.
Alright, hello. It's Mr. Barbera. Here to look at your practice, show what you can do. It should probably say number 1 or something. It's for chapter 1 in CPM. There's a couple things on here I'd probably change if I was remaking this, and I'll tell you about them as we go through. So I'll put my name up here on the top, Mr. B, woo woo, period, I don't need it. All right, so remember, we're going standards-based, scoreless, so you can see your standards at the top of the assessment. It's going to look like this when you get your real show what you can do next Wednesday or whatever day the test is coming up for you. We can look at each standard. Some of these will probably look a little bit different on the actual assessment. One thing is that the first standard sort of gives you some of the answers here for the first couple problems. So that might be look a little different. But we can see standard number 1 says, I can recognize and explain that the probability of a chance event is a number between 0 and 1 that expresses how likely an event is to occur. So the 0 and 1 here is pretty important because we are talking about probability in what I would call decimal form. 0 to 1 as a decimal in a percent would be 0% to 100%. Remember that 1, the decimal 1 or 1 whole is the same as 100%. And if we were talking in fraction form, obviously the denominator of the fraction matters, but if we were saying, let's say like tenths, it would be like 0 tenths all the way up to, I just wrote an 11, but I meant to write 10 tenths. So that'd be an example of how that range would work as a fraction. So you can see decimal, fraction, percent, decimal, percent, fraction. So I also drew a number line down here. Remember, we consider events on a spectrum from never or impossible, it's never going to happen, all the way to something that is always going to happen or is certain. And then right in the center, pretend this is exactly in the middle. Now that I look at it on the screen, I don't know if it's exactly in the middle. But these are equally likely or equally unlikely events. And if I were going to ascribe a number to each of these, and I'm going to go ahead and use the decimal form first, I would start with 0 for my impossible events. I would start with 1 for my certain events. And then 0.5 would be my equally likely or unlikely events. And if I wanted to write these in percent form, 0 would stay the same. This would be 100%. I should have set this up a little bit better. Sorry, it looks a little messy. And this here would be 50%. So, going down to problem 1, it says a probability of 0.1 is. So 0.1, one thing I was telling some students in class is that it might be easier to convert these decimals to percents. So 0.1 we would think of as 10%. And we can see that if we look here on our line, 0.1 is probably going to be somewhere around here. And this is on the left side of equally likely, closer to the impossible side. So it's not impossible because we're not at 0. And it's not going to be equally likely or likely because that would be over in this range over here. So we're going to call this unlikely because it could happen, but it's probably not going to. It's less likely to happen than a 50-50 chance. Moving forward, we already talked actually, number 2, a probability of 1. We could see it right here. It's at the certain end. So if something has a probability of 1, that means it is absolutely certain it's going to happen because it's 100% likely to happen. Like if I said, I'm going to flip a coin and what's the probability I get heads or tails? Well, now that's 100%. It's 1. Because I'm definitely going to get one of the two. Finally, this one, I think I would have rephrased if I was writing this. If it's on the test, I would write this a little bit different. I don't love the way I put it. So I said a probability of 1.5 is, a lot of students in class told me they were thinking this would be certain because it's greater than 100%. And I understand where you're coming from there. If somebody actually told you this was a probability, you would consider it certain. But you're never going to have a probability that's beyond certain. So with that in mind, this is actually going to be considered impossible in terms of that actual probability there. So you're never going to have a probability of 1.5. But I totally understand if you put certain, because you might have thought impossible as just 0, and I didn't phrase this very well. So that's my mistake, Mr. Barbera's mistake. So hopefully you listen to this video and listen to what I just said. And I'll talk about it in class too. Moving on to number 4. This should have had standard 1 on it. Again, early in the year, making plenty of mistakes. It says the range of probabilities fall between which two numbers and why? Well, we already saw up here. We can answer this a couple different ways. We could say from 0 to 1, or we could say from 0 to 100%. And if I was going to write a why explanation, I would probably say because a 0 probability is something, oof, my writing is a little rough here, that will never happen. A 1 probability is something that will definitely happen. And all other probabilities fall in between. So again, because 0 is never, 1 is always, everything else has to fall in between those two things. You can't have something that's more than always going to happen or more than certain to happen. And you can't have something that's less than certain to not happen or less than impossible. So moving on to standard number 2, I'm going to slide back up here for a second. It says I can approximate probability. We kind of abbreviated this standard a little bit for you. So William rolls a fair number cube. I had a hard time saying William there. 700 times. What is a reasonable number of times that a 1, 2, or 3 will appear? Well, we want to think about a number cube. A number cube is a die. So it's a six-sided cube. Okay, instead of drawing it, let's see if I actually have one here. I think it's something like this. So there's 6 sides. Each side has the same chance of coming up. And we're looking at a 1, 2, or 3. So on my number cube, that takes up 3 out of 6 parts. So the theoretical probability of rolling a 1, 2, or 3 is going to be 3 out of 6. And that 3 out of 6 simplifies to, if I divide both of these by 3, 1/2. So 1/2 of the time I expect a 1, 2, or 3 to come up. If I'm going to roll the number cube 700 times, I figure that half of those times is a reasonable estimate for getting a 1, 2, or 3. So I would actually go ahead and just say 1/2 times 700. You can just multiply that probability. And I would expect about 350 times. Like we've talked in class plenty of times, you know this isn't exactly what's going to happen every time. But this is your best estimate based on the theoretical probability. Flipping over, I can't remember if it's a new standard. No, yeah, standard number 3. So I'll stay here for a moment. Standard number 3 says, I can find and compare theoretical and experimental probabilities. I just kind of used both of those words when we were talking about number 2. So remember, theoretical probability is what we expect to happen based on how things are set up, the arrangement of things, before we've done anything. And the experimental probability is what we got after actually doing an experiment. So, and we read this problem here, a bag contains 20 blue buttons and 50 green buttons. You're going to reach into the bag and pull out a button at random 20 times, replacing the buttons each time. That's important because we don't know what to do yet if we don't put the buttons back. And then you get 5 blue buttons and 15 green buttons. So we're going to identify both the experimental and theoretical for getting a blue button. So let's start with theoretical. I said already that theoretical is what we expect to happen based on how things are set up. Probability is always your desired outcomes, the thing that you are looking at. So in this case, getting a blue button, divided by the total number of outcomes. So in theory, we have 20 blue buttons. Well, we do. In reality, we do, but theoretically for the probability. And that is out of 50 total buttons because there are 20 blues and 30 greens. So my theoretical probability would be 20 over 50. I can actually divide this by, well, we could do 10 over 10, a giant 1. And that's going to give me 2 over 5. So a 2/5 theoretical probability of getting blue. I should have labeled this. Probability of blue. And then experimental. Apologize, my writing is not, oh, it's just as clean as it normally is. The probability of blue. We're going to look at what we actually did here. So we got 5 blue buttons. So that was my desired outcome, blue. and I'm going to divide it by the total number of times I drew out of the bag. So I drew 20 times. So it's 5 over 20. We'll divide that by a giant 1 of 5 over 5, and that will give me 1/4. So we can see they're not always exactly the same, but our theoretical probability gives us a good prediction for the experimental. And if we were to do the other ones, just real quick, if you're thinking about it, the theoretical for green would be 30 over 50, or 3/5, and the experimental for green would be 15 over 20, or 3/4. All right, moving on to 3, same standard. So theoretical, experimental, and we're saying there's 16 boys in a class of 20 students. If you choose one student from the class, what's the probability it will be a girl? It just dawned on me that this is a very binary specific question. I apologize for that. We're going to assume that there are 16 boys and the rest of the class identifies as girls. I apologize. So the probability of getting a boy in this class would be 16 out of the 30 total students. And then getting a girl, we're going to assume there's 14 girls, so we would say 14 out of 30. And then we're going to divide those both so we can simplify them. I think I'm going to go 2 over 2. So that'll be 7 over 15. And this would be my simplified probability. Again, sorry about that girl-boy thing. All right, moving on to number 8. There are 70 green and 20 yellow marbles in a jar of 100 marbles. If you choose a marble at random from the jar, what is the probability it will be either green or yellow? So notice I didn't tell you all the marbles, because it actually doesn't matter for the point of this problem. Because since I asked green or yellow, that means I'm going to accept any of those 70 or these 20. So I can actually add those two numbers together, because for the purpose of this probability, they're the same thing. And then I will treat this as 90 out of 100 total. We divide this by a giant 1 of 10 over 10, and I get 9 over 10. And that's probability green or yellow. Equal sign. All right, we're almost there. So let's move on to 9. All right, for the last problem, I don't have it printed out because I just wrote it right now. So you can see it online on Google Classroom. This is the one that I added there. I'm going to go ahead and just kind of describe what it says to you, and we'll write out the work here. So it says, on a given spinner, the probability of spinning yellow, I'll write that as PY, is 1/3. The probability of getting green is 2/5. And the probability of blue is 4/15. What's the probability of spinning green or blue? So, as we talked in class, when we have an or probability, we can just add the two probabilities together, because we're just increasing the size of the portion that we'll take. Like in the case of this spinner, we're willing to take the green section and also the blue section. So we're going to add these together to represent that we're putting these together as a larger space. So I'm going to take probability of green or blue is going to be 2/5 plus 4/15. I need a common denominator, so I'm going to multiply 2/5 by 3 over 3. That's a giant 1. That'll give me 6/15 plus 4/15. And that'll come out to 10/15. I can reduce this now by dividing both by 5. And it's going to be 2/3. Woo! All right. Good luck.